that has two variables, the two variables being time and distance from home. All right, so that time value, because it's on the x-axis, that would be our x variable or our independent variable. The distance from home would be our dependent variable. Just by quickly analyzing the graph, we could see that it would pass the vertical line test, so we could call this y equals f of x. So y as a function of x. All right. So we drew one quick conclusion, and that would be that we are looking at a function here, which is good news. All right, which means that we can draw a conclusion related to distance based off of time elapsed. All right. So in this case, we're looking at a few different components. All right, and we think back to what we talked about yesterday and why this is so out of place in the packet. We talked about whether a function is positive or negative. Or really neither, you know, increasing, decreasing, constant. Actually, I'll throw in neither. Increasing, decreasing, constant. All right, we talked about extreme values. All right, we talked about whether there was a maximum or a minimum. And that took on a couple of different flavors. You know, we had the relative and we had the absolute. All right, so the last thing was the end behavior. Trying to simultaneously take attendance while also doing this, and it's not working. So I'm just going to do the attendance real quick. It's like every 2 words I'm pausing to see example. And I think I got everyone. All right. Okay. So anyway, these are the 4 components that you'd have to address whenever you would write a scenario that would be depicted by the graph. All right. So, you know, you wouldn't know to do that before yesterday. You wouldn't necessarily know what all these things meant before yesterday, which is why this lesson was so out of place. All right, so we're looking at 3 components of this graph. This is what we call a piecewise function or piecewise graph, because it's really 3 separate lines that are pieced together. But I mean, whether you call it that or not is irrelevant at this point. We'll get to that down the line. The whole thing is positive. All right, so I'm just going to highlight the relevant pieces here. We know that it has positives, it has maximums. The end behavior is finite. It doesn't go off to infinity like some of those graphs that we worried about yesterday. You know, like they had arrows on it. This doesn't have arrows on it. So I'm actually going to do a quick strike through on that and say we're not really going to be worried too much about end behavior in this case. Actually, let me just do something real quick. Copy that. I'm just going to pop it down here so I could use it later. Then the whole graph is positive. There's only maximums, there's no minimum values. All right, there's no turning points on the low end. And the end behavior, like I said, is irrelevant in this case. All right. But it doesn't always increase. All right. So the function has positive slopes in 2 different regions. All right. So we have, but not all 3 of them. So it's increasing here, increasing here, decreasing here. All right. Now, just to elaborate on that, we talked about increasing, decreasing yesterday. Increasing meant the same thing as having a positive slope. Slope is positive. All right, for decreasing, we learned that, or we remembered that slope is negative. And that's consistent with the picture. All right. But we want to be thinking about what that means in this context. All right. So slope, by definition, is change in y over change in x. All right. The y equals f of x, or the dependent variable, is distance in home. So change in distance from home per unit of change in time. All right. So this goes back to the discussion related to the DART project, or DART activity, which I still have to give back to you. I'll give it back to you later, later this period. But when we talked about slope in that context, it depended on, well, it depended on what the dependent variable was. So if the dependent variable was horizontal movement, then it was how many feet were traveled per unit of time. All right, vertical movement, same deal. But then there was the change in y, vertical change corresponding to horizontal change. That was feet per foot. All right, so there was a lot of analysis that would go on in there, but we weren't really looking for this type of analysis. We were looking for something a little bit more basic. All right, so when we talk about whether this graph is increasing or decreasing, we don't just say that it goes up. We say that it is increasing, but specifically, what is increasing? The distance from home is increasing based off of changes in time. Or, you know, you can kind of play around with the wording there, but it's for every unit of change in time, the distance is increasing. All right. For every unit of change in time, or for every unit of time, the distance is decreasing. That would be the negative slope situation. All right. So all of that information has to get into the discussion. Also, you have two different intervals over which the function is increasing. They're not increasing at the same rate. You start to think, okay, well, which one's going to be faster, which one's going to be slower? All right. Steeper is going to be a faster rate of change. All right. Steeper corresponds to faster. All right. So a steeper slope is a faster rate of change. So it's increasing at a faster rate. All right. So what happens if it's negative? Well, that just means it's decreasing at a faster rate if it's steeper. All right. So you're looking at the steepness as an indication of how fast the change is occurring. All right. So with all that stuff in mind, and again, this here is just for me. I'm just hanging on to this. This isn't like extra notes or anything. In fact, let me just kind of chuck that onto the next page.
So we go for number 10, for page 10.
Oh, no, I'm not done with it. I'm coming back.
Would we have to indicate, like, so there's the two, so one is noticeably, like, increasing at
like a particular number?
Yeah, like, would you, if we're running a situation, would we say, like, would we have to indicate that it's still increasing, but it does change in the rate at which it increases?
Yes.
Okay.
All right.
So like maybe the joggers start to run slower.
A little bit slower, yeah. All right. So in this case, okay, so let's say we're talking about a jogger. So the person's jogging. They started off at home. All right. So we have, you know, you can give the character a name if you want, but we're going to say a person is jogging. All right, but they're starting off at home, all right, because their distance from home is equal to 0. All right, so this is kind of an important piece here. All right, the person is jogging, but we want to incorporate the idea that they're starting off at home. All right, so a person leaves home and goes out for a jog, but a person is jogging, starting at home is fine too. I just don't, grammar is never, you know. All right, I'll just do parentheses, starting at home. Now, we need a justification. Starting at home, what's the indication that we're starting at home? Well, yeah, there's a point on the graph, but that point on the graph corresponds to an x value of 0, or it has an x value of 0 that corresponds to a y value of 0. All right, that's great, but using function notation, we would say f of 0 is equal to 0. All right, a person is jogging, starting at home. We know that because f of 0 is equal to 0. Moving in a direction away from home. All right, and that's because we're looking at an increasing slope. Well, we're looking at a positive slope. We're looking at an increasing function. All right. So, but we got to get that idea across, all right? The steepness, it's really going to be a relative value, so we won't address steepness until we get to that second piece, all right? So they're moving in a direction away from home, and we know that because the slope is positive, all right? The slope is positive. That means that the distance from home is a positive number per unit of time. The distance from home is increasing. Then the jogger slows down a little bit, but is still moving away from home, jogging away from home. All right, and we know that by two reasons. One, it had to do with the steepness. All right, the slope is less steep. All right, it's still positive, but it's less steep. Slope is still positive, but not as steep. All right, less steep sounded weird. Actually, my whole little narrative here sounds weird. I mean, it's like if I had like an ELA class on a daily basis, maybe I'd have a fighting chance of not having something that reads like on a first grade level. But yeah, it's getting all the points across, and that's what matters. All right. So then we want to get to the downward slope. All right. So the jogger, well, it's kind of hard to tell, but it does look like the slope or the pitch of that last line segment is a little bit steeper than the second one. So I'm comparing this one and this one. All right. This one looks a little steeper. All right. But the negative aspect of it is telling us that the distance from home is decreasing now. All right. So the jogger speeds up, but now moves in a direction towards home. All right. So the jogger speeds up while running toward home, while jogging toward home. The jogger speeds up. But is now moving toward home. And our justification for that is that the slope is negative, which means the distance from home is decreasing. But then throw in there the steepness aspect of it. All right. It's steeper, it's a steeper line than the previous segment. All right. So we could say the line segment is a little bit steeper. For space, I'm just going to say steeper. All right. Then the one last thing we have to incorporate here is the fact that the individual actually got home. All right. So the jogger then arrives at home sometime later. We'll call that time n, because that's the value we've been using this whole time. So I'm just going to pop a little n on the graph here, because we can't just say it was 20 minutes later. It's some unknown amount of time later. So the jogger arrives home n minutes later. And we would justify that by saying that f of n is equal to 0. I'm going to zoom in. I'm actually going to kind of box this up a little bit. So it looks like these are notes, because they are. Kind of shrink it a little bit more. Okay, again, the justification is f of n is equal to 0. And all that means is that if you plug the n into your function, you'll get a 0 as a result. All right, and that should make some sense, all right, based off of the notation. All right. So we've addressed positive, well, indirectly, because there was nothing really to address. The whole thing was above the axis. All right. Increasing and decreasing, we've addressed that. Constant was irrelevant. Right, never flatlined anywhere. All right, we haven't talked about maximum, minimum yet. All right, end behavior was irrelevant. The slope had to do with increasing, decreasing. All right, so the only things that we'd have to talk about would be the extreme values. All right, so it looks like there is a relative maximum at this point here. All right. So it's just a question of how we want to designate that point. All right. It kind of makes sense that we would say, or at least address it verbally, because otherwise we'd have to introduce another variable on the graph. I mean, having an n there already was a little much. But if I say now, okay, let's have like an L, or a Q or something, it's a little too much. All right. But what we can say here is, well, it is a relative maximum. A relative maximum occurs when there's a transition from an increasing slope to a decreasing slope. All right? So we could say there is a relative maximum at the moment when he turns around to go home. When the jogger turns around to go home. All right? There is a relative maximum at the moment the jogger turns around to go home. All right. Yeah, in the past, what I would do for this lesson is let students come up with, and I feel like I'm sort of robbing you of an opportunity here, but it didn't always work out, and I haven't figured out a way to make it work out the right way. But I would say, just what the prompt would say, create a situation that would describe the given graph, and I would get a lot of person was walking away from home. Then they started walking toward home. The end. And it's like, okay, so that was one, all right? Charlie was listening to music while walking away from home. Then changed the song and started walking toward home. The end. And it's like, okay, I think we're missing the point here. We have to get the math terminology in there. It's wonderful that you're coming up with a backstory for Charlie, but we need to get the idea of rates of change, extreme values, positivity, negativity, and so on involved in this. All right. So, yeah, is it like we're writing an essay? Yeah, I guess it's a math essay, but it's also like it's one where you could use crappy grammar and spelling and get away with it because I wouldn't know the difference. Like, so you don't have to worry about me marking up your submission in red, being like, that's an awkward phrasing, or sentence fragment, or oh, you used a semicolon. That's no good there. You know, like I wouldn't know any better. All right, so you don't have to worry about that. You can actually enjoy the process of being able to write a rough draft of an essay, submit that, and know that you're not going to have to revise it 14 times. All right? So, but the key is you have to get those justifications in there. All right. So whenever you write an explanation in math, it's never just the answer. It's the answer and the justification. All right. How do we know they're starting at home? F of 0 is equal to 0. How do we know they're getting that home? F of n is equal to 0.
For that graph, how could you tell that it was a relative maximum and not an absolute maximum?
Oh, well, it actually also is an absolute maximum, right? So in this case, you could have gone either way. So if you made the choice and said absolute maximum, that would have been fine too. Because that's the furthest distance this individual would have gotten away from home, and that would have been your justification. All right. So I can actually throw that in there. All right. So as long as you address maximum or minimum in some capacity, you're good. But if you chose to write about the absolute, you could say there is an absolute maximum also at the moment the jogger turns around to go home, all right? Because that's the furthest distance that individual is away from home, all right? So all right, and we would say f of x is the largest value there at that location. All right. So yeah, I mean, there's a lot going on there, But if you address those important ingredients, and you'll see, based off the examples that follow, that there's hardly ever any instances where you have to worry about end behavior. Actually, in the contextual situations, you're not going to have to worry about end behavior. Just because how do you take infinity, incorporate that into something practical? I mean, it's doable, but it's kind of rare, right? So believe it or not, there are instances where infinity would make sense, but this is not one of them. It's but they're actually more of the theoretical situations. The classic case is the bouncy ball. So if you take a bouncy ball and you know that it has what do they call it? I just lost it. The bounciness. What's the word for bounciness? Okay, well, bounciness is what I'm going for. But no, buoyancy is for. I was thinking that's the word I couldn't get out of my head either. But it's like buoyancy is to water, as blank is to rubber balls that you would bounce on the floor. Spring constants for a spring, like the stretchiness of a spring or the springiness of a spring, whatever. There's a ball. Elasticity, I guess, is probably the word that's closest to what I'm looking for. But anyway, if you drop a ball, its bounciness will only allow it to go up to a certain percent of its original height. And different bouncy balls have different bouncy factors. All right, some of them actually go a little higher than the height that you drop it at. But if you are assuming that it only will reach half of the height of its original height, of its dropping height, then theoretically it would actually never come to a complete rest. All right, because it would always keep going to half again its previous height. So that's a case where it should theoretically bounce for infinity, right? An infinite number of bounces. But practically speaking, it doesn't happen. But you could get an idea of the total amount of height collected if you were to add up all those bounces. But again, that's more of the theoretical rather than the practical. The practical cases, you're not going to really see much involving infinity. All right. So whenever you have to analyze or describe what's happening, you need to really, and I'll get rid of end behavior because it's really not going to be much of a factor. You have to address these three components, all right, at minimum. If somehow infinity works its way in, the idea of end behavior, then by all means. But these three definitely need to be included, all right? The remaining stuff should all be things that you're familiar with, all right? Is it a function? Those should be able to blast through. All right. Is it a function? Yes or no? Does it pass the vertical line test? All right. State the domain and range. Well, how far left and right does it go? How far up and down does it go? Does it include everything in between? All right. Evaluate the function. Interpret the meaning of the value. All right. And then solve for a particular number. All right. So that happens in a couple of cases. So what I'd like you to try to do is answer the problems or try the problems on pages 11 and 12. What do we got? You got like 15 minutes or so, 14 minutes. So you should be able to crank this out. All right. So yeah, take the remainder of the class and work on this, and then tomorrow we're going to start talking about the project for the unit. All right. So yeah. Okay, the rest of the time is yours. I'll stop the recording. One morning, Ben walks along a straight road from his home to a bus stop, a distance of 160 meters. The graph shows his journey on one particular day. So it's saying describe what may have happened, include details, etc. But we'll come back to that in a minute. We'll answer the follow-up questions first because that might feed into our explanation. All right. So is this a function? Well, we know a relation is a function graphically if it passes the vertical line test. So if I can drag a vertical line across the graph in such a way that it never intersects more than once, then it's a function. All right, so this one makes it all the way through the graph without ever intersecting more than once, and so it is a function. So is this a function? Yes. Passes the vertical line test. Oops. The domain and range, the domain is the set of all possible values of x. The range is the set of all possible values of y for which the graph exists. All right, I spent a lot of time with IXL working on this. So anywhere the graph exists, we would indicate the x values. All right, so well, it seems to go from the beginning of the graph grid to the end of the graph grid, which starts at an x value of 0 and ends at an x value of 120. All right, so my domain would go from 0 to 120. All right, there's no open circles or arrows there, so these would be square brackets. All right. Now, the range is the extent of the y values. All right, so on the y-axis, we're looking at y equals f of x. All right, so the lowest and highest possible y values for which the graph exists, and everything in between, appears to be 0 to 160. So that would be my range. All right. F of 30. All right. So f of 30 is a substitution into the function y equals f of x. So they're saying that y is going to be equal to f of 30, which tells me that the x value is 30. So I just need to identify the point on the graph corresponding with an x value of 30. And then the associated y value. That y value would be equal to 60. All right, but the key here is the interpretation. All right, so we look at this and we'd say, all right, well, what does that mean? Well, the x value of 30 is a time in seconds. The y value of 60 is a distance from home in meters. So what this is saying is, after 30 seconds, the distance from home is 60 meters. All right. For number 5, it's saying find the value of n if f of n is equal to 120 and interpret the meaning of this value. All right, so f of n is equal to 120. They're telling us the y value because we know that typically it's in the form of y equals f of x. All right, but what they're saying is that we have 120 is equal to f of n. So they're giving us the y value. All right, the y value is 120. They want us to determine the x value that corresponds with that. But we're really plugging in that dummy variable of n for x. But it's really just basically saying, give me the value of x that corresponds to 120. So on my graph, I would just find the point corresponding with the y value of 120 and then the x value that goes along with that. All right. So that would mean n is equal to 90. So then it's just a matter of interpreting that. All right. So we just got an x value given a y value. So what we're saying here is It's really more like a distance, so we wouldn't start with an indication of time. So we could actually give it the same explanation, but we kind of want to say it the other way around. Like it would take 90 seconds to travel 120 meters, or 120 meters would occur after 90 seconds. But really, it's the same idea. You could actually use the same explanation because it's still the same x variable and the same y variable. It's just we solved for it in a different way. All right. So after 30 seconds, the distance from home is 60 meters. That was number 4. I'm just going to copy paste that. And really just say the same thing, replacing the 30 with a 90 and the 60 with 120. All right, but it really represents the same thing. All right. So now let's go back to number 1 and talk about what might have happened. All right. So kind of a red flag when I'm going over stuff that's related to a quiz that we're going to take, but I can tell people aren't paying attention. But that's all right. That'll show up on the results. So describe what may have happened. We're talking about the 3 ingredients: positive, negative, neither, increasing, decreasing, constant, maximum, minimum. All right. Now, we talked about positive, negative yesterday in the sense that it really doesn't factor into our explanation. All right. Because positive means above the x-axis, negative means below the x-axis. All right. Well, the whole thing's above the x-axis, so I'm not really worried about that. All right. So we could actually kind of disregard that. Increasing, decreasing. All right. So we have increasing here, decreasing, increasing again, increasing, and then constant. Constant would be the flat line. All right. So increasing, positive slope, decreasing, negative slope, increasing, positive slope again. Constant would be the 0 slope or the flat line.
I have a question. On a test or like for regions, would we have to write specific points to which and which? Will it be increasing, or could we do like labeling increasing, decreasing?
It depends. If it was a problem like yesterday where it didn't give us any numerical values, then you could just label it up. But this one does give numerical values, so we would have to be specific.
Okay,
All right. So what we're going to say here, again, is we're going to make our statements, but then we're going to justify it mathematically. All right. So every morning Ben walks along a straight road from his home to a bus stop. All right. So we know that eventually he's going to get to the bus stop. So the assumption is that that's going to be over here somewhere. All right. A distance of 160 meters. All right. So once he gets to a distance of 160 meters, then we're pretty confident that he's arrived at his destination. I mean, that's the whole idea. So we're going to say Ben starts at home. All right, because distance from home in meters initially was equal to 0. We know that because f of 0 is equal to 0. All right. So Ben starts at home, f of 0 is equal to 0. All right. He starts walking away from home for a period of 50 seconds. So walks away from home for 50 seconds. I'm going to move this stuff for the time being, bring it back later. All right, and we know that because the slope is positive from the interval or from the x values of 0 to 50. So over that interval, we know the slope is positive. All right. Now, in terms of his rate of speed, it looks like it's fairly consistent in terms of when he's walking away from home, when he's walking back towards home. All right. So, but we can determine that value. All right. So it's increasing, but we can determine the slope. All right. So the change in y here is 100. The change in x is 50. So for that first piece, change in y over change in x is 100 over 50, which is 2. All right. So he walks away from home for 50 seconds at a rate of 2 meters per second. All right, so we don't have to get into saying, well, I think he's going faster, think he's going slower. We can actually determine how fast he's going and then let the numbers tell the story. All right. Then he walks towards home. Now that's going to be for 20 seconds. Slope is negative. From 50 to 70. All right. Now the rate there, we can figure that out too. We have a change in y. It goes from 100 to 40, which is a change of 60 in the negative direction. All right, so change in y over change in x is negative 60 over 20. So that's negative 3 at a rate of 3 meters per second. I'm going to resize here real quick. All right. We know that there's a relative max at the x value of 50. All right. There is a relative maximum at 50. Slope changes from positive to negative. All right, if you ever have a sign change in slope, that means you have a relative extremum. All right, increasing to decreasing or slope going from positive to negative, that indicates a relative maximum. All right, then he walks away from home. Well, it's from 70 to 100, so that's for another 30 seconds. So walks away from home. All right, so 70 to 100 seconds, so for 30 seconds. All right, and again, the slope is positive. From 70 to 100. All right, but again, we could also figure out what that slope is. And because it's a numerical problem, we need to. All right, so we have a change in y value. It goes from 40 to 160. So change in y over change in x. So 40 to 160 is a change in 120. Change in x was 30. So that's 4. That's a value of 4. All right, so at a rate of 4 meters per second. I'm going to zoom in. All right, so at a rate of 4 meters per second, but we also know that there's a relative minimum because the sign changes from negative to positive. All right, and that happens at 70. So there's a relative minimum at x equals 70. Slope changes from negative to positive. All right. And then we just have to address constant. All right, so we have our extreme values. We talked about where he started his trip. He's going to end his trip when he arrives at his destination. All right. So Ben arrives at the bus stop. I'll just kind of tuck that over here. Ben arrives at bus stop. I don't know why he's walking his dog to a bus stop, but whatever. Maybe he's picking up a sibling. All right, after, well, it starts to flatline at 100 seconds, after 100 seconds. All right, and we know that because the slope is now 0. And that means he stopped moving. All right.
So for the test, would we have to go?
Quiz.
For the quiz, would we have to go, like, would we have to label to the same extent we did here?
Yeah. That's why I wanted everybody's focus and attention. Yeah, it's that important.
Is the quiz only questions like these, or are there like multiple choice?
Oh no, there's multiple choice, but they're quick hitters. Like, which of the following is a function? You know, and you just look, it passes the vertical line test, done, quick and easy. You know, that's the idea anyway.